For over a century, scientists have hunted the ultimate key to the universe, a single theory that could unite everything: gravity, quantum mechanics, time, and space itself. Einstein thought he was close. String theorists believed they had it. Each time the dream slipped through their fingers. Why? Because every answer reveals a deeper contradiction, as if the universe itself is hiding the truth behind layers of impossible math. Relativity works perfectly for stars and galaxies. Quantum physics rules the world of atoms, but together they break apart. Two masterpieces that refuse to share the same stage. Still, physicists can't stop trying, not because they're obsessed with equations, but because failure might be the only path to understanding what reality truly is. So take a breath and step into the theory that keeps even the brightest minds awake at night. Close your eyes for a moment. We're standing beneath a sky that has never fallen silent, a dome of questions stretching across time. It is the same sky that once made the Greek philosophers look upward and ask, what if everything comes from one thing? One breath that moves through every star, every atom, every mind. They called it Arch, the first principle, the thread beneath all patterns. Thousands of years have passed, yet that whisper still travels through the night. You can almost hear it between the faint pulses of starlight, a rhythm older than words. Imagine the universe as a vast orchestra, galaxies deep as cellos, atoms shimmering like violins, gravity keeping the slow, patient beat. And hidden somewhere in that music there should be one melody, a harmony simple enough to bind every motion, every scale, every silence. But the song never quite resolves. Each instrument drifts, stretches, disagrees. When one section finds order, another falls into chaos. The dream of a single score, an equation that plays the whole universe, remains a vibration at the edge of hearing. We have been climbing toward that sound since the first circles were drawn in sand. Every generation adds another step to the ascent, from the geometry of the ancients to the clockwork of the planets, from faith in harmony to the mathematics of motion. Now, as you and I pause at the threshold of modern science, we can see two figures standing in the half-light. One is Isaac Newton, holding the laws that stitched heaven to earth. The other is Albert Einstein, bending space and time into curves of meaning. They are not the destination, but the signposts, points of reference on a staircase that still rises. Take a slow breath. The orchestra is tuning again. Somewhere beyond the silence, the next note waits. We are still here, balanced between stars and numbers, between what we can measure and what we can only sense. The dream of unity begins to take shape, not as a story, but as a relationship, a rhythm that the universe repeats in every scale. When mass exists, space responds. That was the quiet revelation behind Isaac Newton's law of gravitation. He discovered that the same pull bringing an apple to the ground is what keeps the moon in its endless fall around the Earth, a silent attraction linking every object from a grain of sand to the sun itself. In plain language, the greater the mass, the stronger the pull, and as the distance doubles, that pull fades by 4. It is a symmetry written into nature, a law of proportion. Once revealed, it became the master key of motion. Planets obeyed their orbits with clockwork precision, comets returned on schedule, and the same mathematics seemed to guide both heaven and earth with divine consistency. For a time it felt as if the cosmos had chosen elegance. Everything could be known, measured, described. Each star was a note in a perfect composition. But then tiny dissonances began to hum at the edge of certainty. Mercury's orbit shifted slightly, a few arc-seconds each century. Light bent around the sun a little more than expected. The formula worked, but not completely. Nature, patient and subtle, was whispering that gravity might not be a force at all, but something deeper, a curvature, a structure, a presence. Centuries later, that whisper found its answer. Albert Einstein reimagined space and time as a single pliable fabric. Gravity, he said, is not a pull, but a bend, the geometry of reality responding to mass and energy. Mass tells space-time how to curve, curved space-time tells mass how to move. Imagine a sheet stretched tight. Place a heavy sphere upon it and the surface warps. Smaller marbles rolling nearby follow those curves naturally. They are not being pulled, they are simply moving straight through curved space. Planets orbit stars. Light deflects near massive bodies. Time itself slows in the deep valleys of gravity. Einstein's equations healed the gaps Newton could not. They explained Mercury's drift, predicted starlight bending during eclipses, and revealed that the universe is not static but alive, a continuous flexible fabric where time and distance shift together. Its accuracy was breathtaking, its beauty undeniable, and yet perfection never lasts. General relativity governs the vast galaxies, black holes, the cosmic web, but collapses in the quantum realm where geometry frays into probabilities and uncertainty reigns. Two truths precise yet incompatible, like instruments playing in different keys, so we stand between Newton's clarity and Einstein's curvature, each right within its domain, each incomplete. The bridge they built still holds graceful, luminous finite. There is a quiet rhythm behind every discovery, a rise, a crest, and a resistance that follows. Each time we reach for completion, the universe answers not with closure but with contradiction. When Newton's perfect heavens fractured under Mercury's subtle defiance, the crack did not mark an ending, it opened a door. And that door would swing again centuries later for Einstein. Einstein's cosmos was continuous and complete. Every event traced back to a cause, every motion followed reason. It was a reality built on smooth geometry, where time and space blended into an elegant, predictable whole. Yet while he was sculpting that curvature of the universe, another kind of law was quietly emerging from the microscopic. A law not of certainty, but of chance. In the quantum world, particles did not choose a single path, they traveled all paths at once. Observation itself determined what was real. The universe at small scales no longer behaved like a clock, but like a sea of possibilities, collapsing into one outcome only when watched. Einstein could not make peace with that. God does not play dice, he said, not as defiance, but as devotion to order. For him, uncertainty was not a frontier, it was a flaw in understanding. He believed that beneath the noise of probability lay a deeper structure, a harmony we had not yet heard. So he searched year after year for a way to merge the quantum with the cosmic, for a single framework that could explain both the spin of electrons and the orbit of stars. But nature refused to be cornered. Every equation that tried to unite those two realms unraveled. Mathematics exploded into infinities. The smooth curves of space-time could not contain the jittering foam of quantum behavior. The more we tried to press them together, the more they seemed to resist, not in defiance, but as if protecting their own domains. Perhaps the failure was not in the math, but in the metaphor. Maybe the universe never intended to speak with one voice. Maybe it sings in chords, relativity providing the low, steady bass of gravity, quantum mechanics, flickering in the treble of uncertainty. Together they form harmony, not identity. And what we call failure is simply the dissonance that appears when we insist that only one melody can exist. Einstein's refusal then may not have been stubbornness, but faith that the cosmos remains readable, that coherence must exist even when hidden from view. His decades of struggle were not wasted. They were the first signs that unification might require a different kind of thinking, not reducing but reframing. To see not one law but two perspectives coexisting as complementary halves of a deeper order. And now we stand where he once stood, between the smoothness of the stars and the chaos of the quantum. From afar the universe looks serene, up close it quivers with randomness. Ahead lies the frontier where both truths collide, where the bridge between them begins to tremble, and in that trembling the next discovery waits. We pause here between clarity and contradiction. Behind us lies the calm geometry of Einstein's cosmos, smooth, continuous, exact. Ahead the air begins to flicker. The shapes we trusted start to dissolve into probabilities, and the familiar rhythm of cause and effect fades into a softer uncertainty. We have followed the arc from Newton's order to Einstein's curvature, and now the path begins to split. One road leads through the vast domains of galaxies and black holes, the other dives inward into the restless sea of atoms and quanta. Each claims to describe the same universe, yet neither can explain the other. This is where the real tension begins, where the stage of space-time meets the dance of the invisible. The harmony is about to fracture, and the search for unity will enter its most fragile terrain. We now stand where the bridge begins to shake. Two visions of the same universe stretch out before us, both true, both incomplete. Each describes reality with precision, but they speak in different tongues. General relativity, or GR, is the language of the immense. It deals with galaxies, black holes, and the cosmic web that spans billions of light years. In this view, space and time merge into a single smooth geometry. Matter bends that geometry, and geometry tells matter how to move. Everything is continuous, flowing, curved. Equations are elegant, like the lines of a perfect sphere, every planet's orbit, every photon's path traced by the fabric of spacetime itself. Quantum mechanics, or QM, lives at the opposite extreme, the microscopic. Here reality is granular, unpredictable, alive with uncertainty. Particles behave not as points but as clouds of probability. Instead of curves, there are jumps. Instead of certainty, only chances. The act of observation doesn't just reveal what is there, it changes it. Energy comes in discrete packets or quanta, each transition a tiny step rather than a smooth glide. If GR is the continuous flow of a river, then QM is the shimmer of sunlight dancing on its surface, both parts of the same scene but impossible to describe with one equation. Or think of them as two instruments: relativity, the deep resonant cello; quantum mechanics, the bright unpredictable violin. Together they form the score of the universe, yet they never seem to tune to the same key. In the cosmic scale, GR predicts the expansion of galaxies, the warping of light, the merging of black holes whose masses may reach tens of solar masses. It describes time slowing near a gravitational well, light stretching into red as it climbs out of it. Everything is continuous, a smooth curvature extending without break. At the quantum scale, things tremble with randomness. An electron can exist in many states at once until we look. The nucleus of a single hydrogen atom, a proton, exists in a haze of probabilities described by the wave function, PSI. Here, geometry collapses into uncertainty, and the idea of a smooth space no longer makes sense. Instead of curves, we have quantum jumps. Instead of trajectories, we have possibilities. Both theories work flawlessly in their own realms. Every GPS signal, every image from the James Webb Space Telescope relies on Einstein's geometry of time and space. Every semiconductor, every MRI scanner, every star's nuclear furnace depends on the quantum rules that govern atoms. Neither can be dismissed. Both define the modern world. And yet the moment we try to ask a question that requires both how gravity behaves inside a black hole or what happened at the first instant of the Big Bang, their equations begin to break. Relativity insists on smooth continuity. Quantum mechanics insists on jittering granularity. Between the two, the mathematics produces infinities numbers, without meaning like static on a cosmic radio. This is the fracture line of physics, the fault where the deep cello and the sharp violin lose harmony. Somewhere here a new language must exist, one that can let both melodies play at once. There are places in the universe where both of nature's languages, the smooth geometry of relativity and the restless pulse of the quantum world, are forced to speak at once. And there their words begin to break apart. Inside a black hole, gravity deepens until space itself curves inward and time slows to a crawl. The pull becomes so strong that even light moving about 300,000 kilometers every second cannot escape. Relativity predicts that everything drawn in will compress into a single point, infinitely dense, infinitely small. But infinity is not a description of reality. It is a sign that the mathematics has gone blind. Quantum theory refuses to accept such blindness. It says that matter and energy cannot be perfectly smooth. They are made of quanta indivisible packets with natural limits. Even in a perfect vacuum, quantum fields tremble. Particles flicker in and out of existence like ghosts appearing, vanishing, reappearing, a quiet storm at the foundation of space itself. If that storm is everywhere, then nothing, not even a black hole, can be truly smooth. But when we try to join these two visions, relativity's curved stage and quantum's restless foam, the numbers collapse into chaos. Every equation trying to describe both worlds at once explodes into contradictions. Zero meets infinity. Cause loses sequence. The geometry of space-time twists beyond definition. The mathematics doesn't simply fail, it unravels. At the boundary of a black hole, this conflict becomes visible. The event horizon, that invisible surface where nothing returns, is supposed to be absolute. Yet according to quantum theory, a thin breath of radiation escapes from it. Tiny pulses of energy, hawking radiation, slowly steal mass from the black hole itself. If that is true, then what happens to the information about everything that fell inside relativity says it vanishes forever. Quantum mechanics says information can never be destroyed. The universe cannot satisfy both. The same fracture appears at the beginning of time, when everything we see, every atom, every galaxy, was compressed into a region smaller than a single proton. Relativity describes a smooth beginning, a cosmic expansion from a singular point. Quantum theory, however, sees turbulence a chaos of probabilities flickering faster than time can measure. The two pictures cannot coexist, and the result is the same impossible infinity. In those moments at the core of a black hole or the dawn of creation, our laws no longer describe the universe. They describe the limits of human understanding. The equations dissolve into silence. It is as if the cosmos was saying, "You've come this far. To go farther, you must change the language itself." Imagine two instruments trying to play the same note but tuned to different keys. As their tones overlap, harmony turns to tremor. That tremor is the sound of physics breaking. It rises wherever gravity and quantum uncertainty try to share the same stage, a vibration not of matter, but of meaning. Physicists call it the incompatibility problem. It marks the edge of everything we know. One theory describes the very large, the other, the very small, and neither can speak the other's truth. Here at this peak of contradiction, our dream of a unified theory meets its first great silence. The bridge between the infinite and the uncertain hangs over an abyss of untranslatable laws. And yet even this failure is a kind of signal. It tells us that the universe is not wrong, only our understanding is incomplete. The universe is not contradicting itself. It is we who ask it to speak in a single tongue. Every framework we build is an attempt to compress the vastness of nature into human logic, and logic by its very shape has limits. General relativity and quantum mechanics are not rivals. They are siblings describing different magnitudes of existence. Relativity governs the large, the motion of planets, the bending of light across billions of kilometers, the slow rhythm of clocks under the pull of gravity. Quantum theory rules the small, the trembling inside every atom, the spontaneous birth and death of particles, the delicate probabilities that underlie what we call matter. Each system is flawless inside its own territory. Each has been verified with exquisite precision, but neither can fully contain the other. When we try to extend one language into the domain of the other, its grammar collapses. Spacetime curves smoothly in Einstein's equations, but at the quantum level, that smoothness disintegrates into noise. Quantum theory depends on discrete events, but in curved space-time, the notion of a fixed event loses meaning. It is not the universe that fractures it, is our syntax. This is why the clash between the two is not truly a war of ideas, but a misunderstanding of scale. Every law of nature is written for a particular domain. Each law says, "Here and only here I hold." Outside that domain, new conditions take over. In that sense, our equations are like lenses. Relativity is a telescope vast and serene, made to observe the motion of galaxies and the stretching of the cosmic web. Quantum mechanics is a microscope sharp and restless, made to reveal the fluctuations that dance beneath the fabric of matter. Both reveal truth, but only from their proper distance. A telescope cannot resolve the grain of an atom. A microscope cannot frame the birth of a galaxy. Each becomes blind in the other's realm. The incompatibility is not a defect. It is a signpost. It tells us that truth is stratified, that reality may be woven from layers of order, each obeying rules that fade or transform at another scale. Perhaps this is how the universe maintains its coherence, by allowing its laws to overlap but never completely merge. Where gravity dominates, probabilities dissolve into certainty. Where quantum behavior rules, geometry becomes irrelevant. Only at their border, in the core of black holes or at the dawn of time, does their conversation break into static. That static is what we hear as paradox. The lesson is quiet but essential. Neither theory fails. Both declare their boundaries. Every equation carries an implicit humility. This truth holds until the world changes scale. In that humility lies progress itself, because every boundary we discover becomes the edge of the next discovery. And so, the incompatibility problem is not a wall, but a mirror showing us that unification may not mean sameness, but resonance across domains. To find the next step, we must turn toward the one force that has refused every invitation to fit inside the quantum order. The patient outsider that shapes the stars and bends the stage on which all others perform the gravity itself. We have reached the line where both maps end. Behind us, the twin architectures of relativity and quantum mechanics still stand precise, elegant, and proud, yet their edges fade into mist. Each law remains intact within its own horizon, but beyond that horizon there is no language left. Only silence. And in that silence, a question waits. If the universe can be described so perfectly in parts, why does the whole remain beyond reach? Why does every attempt to fuse the two languages turn clarity into chaos? Perhaps the answer is not hidden in equations, but in the nature of separation itself. Relativity teaches that the cosmos is continuous, a single smooth geometry, where matter tells space how to curve and space tells matter how to move. Quantum theory insists that reality is grainy, a restless sea of discrete events, each governed by chance. Between those visions lies not contradiction but a rhythm. Continuity and discontinuity, order and fluctuation, like two alternating pulses in the heart of existence. Maybe the universe sustains itself through this alternation, a balance that keeps it from collapsing into either total certainty or total randomness. Relativity preserves coherence at large scales. Quantum effects preserve creativity at small ones. Without the first, the cosmos would fall apart. Without the second, nothing new could emerge. We live suspended between them, a species made of matter yet ruled by probabilities, anchored in gravity yet flickering in time. At this boundary, every scientific question becomes a philosophical one. Where do laws end and patterns begin? Are contradictions signs of error, or signs that the universe is richer than logic allows? Perhaps incompatibility is not failure, but design a structural safeguard that prevents any single theory from claiming completeness. The cosmos may demand plurality, not unity. Or maybe unity itself exists, but only from a higher dimension of understanding, one we're not yet able to see. Still, one force stands apart from the rest. While electromagnetism and the nuclear forces fit beautifully within the quantum framework, gravity remains outside, unmoved, indifferent to every attempt at quantization. It shapes the orbits of galaxies, governs the collapse of stars, yet it refuses to reveal the quantum particles that should carry its influence. It holds everything together, and yet it is the one that does not belong. To move forward, we must follow that anomaly. We must ask why the weakest force in the universe has become the strongest obstacle to understanding it. This is the paradox that pulls modern physics into its next era, the outsider force that defines the inside of everything. We stand now at a point in physics that almost feels complete. Three of the four fundamental forces, electromagnetism, the weak force and the strong nuclear force, already share a single mathematical home. Together they form what physicists call the Standard Model, a framework that describes nearly every measurable interaction in the microscopic world. Within this structure, each force speaks the language of quantum fields. Particles are no longer hard spheres, but ripples, excitations in invisible fields that fill space. The photon carries light and electromagnetic energy. The W and Z bosons govern radioactive decay, while the gluons bind the quarks inside protons and neutrons. Every movement, every transformation of matter that we can reproduce in an accelerator fits these rules with astonishing precision. In laboratories across the planet, from Geneva to Chicago, beams of protons collide at nearly the speed of light, about 300,000 kilometers per second, and the debris they produce follows the equations as if nature were reading from the same page. The Standard Model works so perfectly that at times it almost feels finished. Almost. Because there is still a silence in the symphony. Three sections of the orchestra perform in perfect quantum harmony, yet one instrument, the deepest, slowest bass, never joins in. That missing sound is gravity. Einstein's general relativity describes gravity as the bending of space and time themselves. Mass tells the stage how to curve, and curvature tells mass how to move. It is continuous, geometric, serene, a vision of the cosmos written in smooth equations. But when we try to merge this with the jittering, probabilistic world of quantum mechanics, the mathematics breaks. The moment we attempt to express gravity in the quantum dialect, infinities erupt. Physicists have long imagined a messenger particle, a hypothetical graviton that would carry the gravitational force the way photons carry light. In theory, these quanta would ripple through the fabric of spacetime, connecting all masses across the universe. But when researchers tried to calculate how such particles would behave, the numbers refused to settle. Instead of converging to finite answers, the equations exploded, producing values without limit. To make the theory work, one would have to subtract infinity from infinity again and again until meaning evaporates. It was as if the mathematics itself rejected the idea. Some interpret this as a clue. Maybe gravity cannot be reduced to particles because it is not a force in the same sense as the others. Maybe it is geometry, or even something emergent, a property that arises only when space and matter exist together. If that is true, the Standard Model may not be the final word, but a chapter within a larger book. For now, gravity remains the outsider, the one field that refuses to quantize, the one voice that will not join the chorus. Its absence leaves a dissonance at the heart of physics, a low note that hums beneath every experiment, reminding us that unity, however close, is still incomplete. When gravity refused to join the quantum family, physicists began to imagine new ways of describing it. If the equations of a quantum graviton collapsed into infinities, perhaps the problem was not with the math, but with our assumptions about space itself. Maybe spacetime is not a continuous fabric at all. Maybe it is woven from threads so fine that our instruments cannot yet detect them. This is the spirit behind loop quantum gravity, often called LQG. Instead of treating spacetime as smooth, LQG suggests it is built from tiny discrete loops, quantum-sized rings of geometry. Each loop represents a fundamental grain of space, a pixel in the cosmic screen. Just as matter is quantized into atoms, space and time themselves may also come in smallest units. Between those units lies nothing, no smaller distance, no shorter duration. At this scale, the universe would not appear as a flowing continuum, but as an intricate web of interlocking loops. Each intersection defines an area, each link defines a volume. Together they form a network known as the spin network, an architecture where gravity arises from how these loops connect and twist. In this picture, the curvature of space is not an abstract shape, but a measure of how many loops cluster in a region. It is geometry written in quanta. The theory has elegance. It removes the infinities that plague conventional quantum gravity and predicts that at the smallest possible scale around the Planck length, roughly 1/10 billion trillion trillionth of a meter, the idea of continuous space breaks down. Even the inside of a black hole might not collapse into a true singularity, but into a dense knot of quantum geometry. Space could rebound instead of vanishing, leaving behind a trace of what once fell in. Yet loop quantum gravity faces a different difficulty: isolation. It explains gravity but not the other forces. While the standard model unites electromagnetism and the nuclear forces through a shared quantum language, LQG speaks a dialect of its own. It does not naturally include the particles or interactions that make up atoms, light or radiation. It solves one problem by creating another completeness without connection. From here, a bolder idea emerged. What if gravity is not a fundamental force at all, but a side effect, a phenomenon that emerges from deeper hidden principles? Some physicists suggest that gravity might arise from the way information is entangled at the quantum level. Imagine every bit of space carrying a pattern of information linked with every other bit. The tension within that vast web of entanglement could produce the effect we experience as gravity, not as a fundamental push or pull, but as a statistical drift of information-seeking balance. In that view, gravity becomes the whisper of quantum information organizing itself. Space-time would not exist first. It would appear only when information connects in the right way. The cosmos then might not be built from matter or fields, but from relationships, from the invisible bonds that hold information together. If this is true, the unification we seek will not come from forcing equations to merge, but from understanding how reality itself emerges. A shift from geometry to information, from matter to meaning. And in that shift, perhaps a new kind of physics waits, one that listens not to particles but to patterns. Black holes were once seen as the ultimate success of Einstein's geometry, a place where gravity's strength bends the stage of space-time until it folds in on itself. Nothing escapes, not even light. They were the clean, silent punctuation marks of the cosmos, where matter ends and geometry takes over. Then, in the 1970s, Stephen Hawking asked a question that disturbed the calm surface of this idea. If quantum mechanics applies everywhere, he reasoned, then even near a black hole's edge, the event horizon particles should still flicker in and out of existence. The vacuum cannot stay empty. It trembles with possibility. Pairs of particles appear for a moment, one falling inward, one drifting away. The escaping one would carry energy, and over time that energy loss means the black hole itself must shrink. From this, Hawking predicted something extraordinary: black holes are not truly black. They emit faint heat radiation so weak that it would take billions of years to notice, and through this slow evaporation even the heaviest black hole would one day vanish. The strongest expression of gravity would paradoxically erase itself. But this revelation carried a deep contradiction. Quantum mechanics insists that information can never be destroyed. Every particle, every interaction carries a pattern, a record of how the universe has evolved. In principle, those records can be traced backward. Nothing fundamental ever truly disappears. Yet Hawking's radiation seemed to say otherwise. If a black hole evaporates completely, what happens to the information about everything that fell in the atoms, the fields, even the structure of quantum states all gone? The universe, once perfectly reversible, would lose its memory. That impossibility became known as the information paradox. Relativity allows information to fall beyond the horizon, but quantum theory refuses to let it die. The two laws of nature, each flawless on its own, collide at the edge of the black hole and tear the logic of physics in half. For decades, scientists have searched for a reconciliation. Some propose that information leaks out encoded in the subtle variations of Hawking's radiation. Others believe it never leaves at all, that it is stored on the thin surface of the event horizon, like a hologram projecting the interior from the boundary. Still others imagine new geometries, wormholes, or quantum bridges that carry information elsewhere unseen. No matter the interpretation, the message is haunting. The same gravity that holds galaxies together is the one that shatters our most trusted equations. The same force that unites stars and planets forces our theories to contradict themselves. We have followed gravity to its deepest silence, from Newton's pull to Einstein's curve to Hawking's paradox. Each step has revealed more of its mystery, yet the closer we draw, the more it slips from our grasp. The equations bend, the concepts fray, and the universe seems to whisper. You are asking the wrong kind of question. Perhaps gravity is not something to be contained within quantum theory, nor a force that needs a particle to exist. Maybe it is a shadow, a reflection of something deeper that underlies both space and matter. If so, what we call the universe might only be a vibration of something more fundamental, a pattern that resonates through dimensions we cannot see. Physicists have long suspected that what we perceive as particles may not be points at all, but tiny strings of energy, vibrating filaments whose tones determine everything that exists. Each vibration would create a different note, one for an electron, another for a photon, another for the elusive graviton. In this view, the universe is not a collection of objects, but a grand instrument, a multi-dimensional harp whose strings sing reality into being. This idea is more than poetic. It offers a mathematical way to unify gravity with the other three forces, something that has eluded science for nearly a century. But the price of such beauty is complexity. To make the equations consistent, the strings must vibrate in more dimensions than we can perceive, 10 or even 11 dimensions hidden curled into spaces too small for light to reach. And yet this framework carries a quiet promise. Where geometry breaks and gravity rebels, string theory might restore harmony. It whispers that all of creation could be woven from one substance, one motion, one rhythm. A theory where the laws of the large and the small finally sing the same song. Take a slow breath. The path of gravity ends here, but a new vibration begins to rise, a faint hum at the edge of understanding, inviting us to follow the sound. If gravity resists the quantum framework, perhaps the fault lies not with gravity, but with our picture of matter itself. For decades, physics has treated the universe as a mosaic of indivisible points, tiny objects with no size, only mass and charge. Yet at the smallest imaginable scale, this picture begins to crumble. String theory proposes a different vision. It replaces those point-like dots with microscopic filaments of pure energy, each one endlessly vibrating. These filaments are unimaginably small, about 10 to the minus 35 meters long, and they vibrate in many possible patterns. Each mode of vibration corresponds to a different particle. A slow, gentle oscillation gives an electron. A higher frequency pattern yields a photon. Another special vibration produces the long-sought graviton, the particle that would carry gravity's influence. Under this single assumption, the diverse zoo of subatomic particles becomes a unified family. The universe ceases to be a collection of independent objects and instead turns into a grand composition, one instrument playing different notes across the scale of existence. Matter and light attraction and radiation all become harmonics of the same string. The mathematical structure behind this idea is astonishingly rich. It links quantum mechanics and relativity within a single geometry, where vibration replaces mass as the fundamental property of reality. Instead of asking what something is, we ask how it moves. Every entity, electron, quark, or photon is simply a different rhythm in the same cosmic dance. But there is a condition hidden within the equations. For the mathematics to remain self-consistent, the strings cannot vibrate in only 3 spatial dimensions. They require more room, 10, sometimes 11 dimensions in total. The additional directions are believed to be compact, curled upon themselves so tightly that even light cannot reach inside them. Picture a thin wire seen from far away. To the eye, it seems like a single line, yet up close it has a circular thickness, an extra direction wrapped around itself. In the same way, the hidden dimensions of string theory could be coiled within every point of space far too small for any experiment to detect. No accelerator on Earth can reach the energy needed to probe such scales. The extra dimensions remain invisible, inferred only through mathematics. Still, the coherence of the equations is so powerful that many physicists trust them as a signpost. A deeper layer of the universe must exist, even if it is beyond reach for now. If these vibrating filaments are real, they explain not only matter and energy, but also gravity itself. One principal oscillation would underlie all interactions. Every proton, every burst of starlight, every curvature of space would be a variation of a single theme, energy in motion. For centuries, science has trusted a quiet intuition that the universe in its deepest form must be beautiful. From Newton's clean equations to Einstein's smooth geometry, beauty seemed to be the signature of truth. When the mathematics looked elegant, when the symmetry felt complete, it often turned out to be right. String theory continues that tradition, but it also exposes its danger. Its equations shimmer with perfection, a single framework uniting gravity, matter, and energy within the dance of vibrating strings. 10 or 11 hidden dimensions curl themselves into invisible folds, forming shapes of extraordinary mathematical harmony. And yet, for all its elegance, the theory offers no prediction that the laboratory can touch. No collision, no detector, no telescope has yet heard the song it promises. The risk becomes clear. When beauty seduces us, we may stop listening for the rough, imperfect notes that reality insists on playing. History has seen this before. The Greeks once believed celestial motion must follow perfect circles because only circles were worthy of the heavens. It took Kepler to show that the planets move in ellipses less perfect yet true. Our minds crave order. Nature, meanwhile, only obeys itself. So perhaps the lesson is humility. A beautiful equation can guide us, but it cannot compel the universe to agree. When we fall in love with symmetry, we risk mistaking elegance for evidence. The standard model, though inelegant and patched together, describes experiments with astonishing precision, while string theory, vast and graceful, still waits in silence, a masterpiece without a performance. Maybe truth and beauty are not twins, but distant cousins who meet only on rare occasions. The universe may be less like a finished sculpture, and more like an unfinished sketch, messy, layered, and alive. The pursuit of harmony has brought us to the edge of imagination, but the next step must leave the blackboard behind. To move forward, we must listen not to what feels elegant, but to what can be measured. For a long time, physics has moved by faith in harmony, the belief that the universe must follow elegant laws. But harmony without sound is still silence. String theory hums with mathematical grace, yet the instruments of experiment hear nothing. It is a reminder that beauty alone cannot close the gap between dream and data. Every age of science faces this turning point. A theory begins as vision then must face the light of measurement. We have mapped the mathematics of the invisible, but now the universe asks for something more tangible, for evidence that can be seen, weighed, or detected. Between blackboards and laboratories lies the frontier of truth. Perhaps the next breakthrough will not come from deeper abstraction, but from precision, from experiments capable of sensing the faintest tremors of space and time. Gravitational waves, quantum interference, and entanglement tests at microscopic scales may soon begin to whisper what equations alone cannot confirm. The era of pure theory fades into the era of observation. What was once written in symbols must now speak through instruments. We leave behind the elegant silence of strings and turn toward the delicate hum of reality itself, where data, not design, decides what is true. Next, we enter that threshold, the experimental dawn of quantum gravity, where science finally begins to listen for the universe's reply. In the silence of a laboratory, the search for quantum gravity no longer unfolds through distant galaxies or massive colliders, but across a tabletop so small it could fit in the palm of your hand. Here in this still space, scientists are trying to test the weakest of all forces, gravity, at the smallest possible scale. At everyday levels, gravity seems omnipresent and powerful. It keeps our feet on the ground and holds planets in orbit. But when we descend into the quantum world, it fades almost to nothing. Between two particles, its pull is so faint that even a single vibration from the surrounding air could drown it out completely. Measuring it directly in this regime is like trying to hear the fall of a snowflake during a thunderstorm, and yet this is precisely where physicists now focus their attention. The goal is simple in concept but monumental in execution: to see whether gravity itself can produce quantum entanglement, the mysterious connection between particles that allows them to share a single state, no matter how far apart they are. In classical physics, forces act through continuous fields, gravity curves, space electromagnetism flows through lines of influence. But in quantum theory, every force is mediated by particles. Light arises from photons. The strong and weak forces emerge from gluons and bosons. If gravity too has a quantum carrier, a graviton, then it should be capable of entangling objects through purely gravitational means. This is the essence of the tabletop frontier. Two microscopic masses, each isolated in near-perfect vacuum, are placed close enough that the only possible interaction between them is their mutual gravitational pull. Every source of disturbance, air molecules, magnetic fields, thermal motion, is eliminated. The environment is cooled to near absolute zero. The apparatus rests on vibration-isolated platforms that float like rafts upon still water. If under such pristine conditions the two tiny masses become entangled, if their quantum states correlate in a way that cannot be explained classically, then it would mean gravity itself must be quantum in nature. The experiment is delicate beyond imagination. A whisper of heat, a flicker of light, even the gravitational influence of a researcher walking nearby could undo months of preparation. Each test requires the precision of stillness, the art of silence. To let gravity reveal its quantum side, scientists must first remove the noise of an entire world. Imagine standing beside such a setup, two metallic spheres barely visible under the dim light of a cryogenic chamber suspended in vacuum. Between them stretches not a wire, not a field line, but emptiness, the faint curve of space-time itself. Every vibration that reaches them is measured, filtered, or frozen out. It is an experiment built upon quiet listening for the gentlest murmur of the universe. If the entanglement appears, it would be a profound revelation. It would mean that spacetime itself can carry quantum information, that gravity, the oldest of all forces, speaks the same probabilistic language as the rest of nature. But if no entanglement is found, it would suggest that gravity stands apart, that it remains even now a purely classical relic in a quantum world. Either outcome reshapes physics. Success would open a door toward the long-sought theory of everything. Failure would force us to rethink what quantum even means. For now, the experiment continues silent and patient. Each cooled chamber, each isolated sphere becomes a question suspended in the void. Does gravity too shimmer with uncertainty, or is it the one part of reality that remains perfectly still? For more than 3 centuries, gravity has appeared to follow a simple pattern. Its pull fades with distance, and it fades quickly. If you double the separation between two objects, the attraction becomes 4 times weaker. This rule, often called the inverse square law, has guided astronomy and engineering since the era of classical mechanics. It works for falling apples, orbiting moons, and even the dance of planets around their stars. But what happens when we probe distances not of meters or kilometers, but of micrometers, a thousandth of a millimeter thinner than a human hair? At such tiny separations, some theories suggest gravity might deviate slightly from the familiar rule. In ideas inspired by higher dimensional physics, gravity could leak into hidden directions of space. If that leakage exists, the force at very short range might not weaken exactly as distance squared, and the difference, though small, would be measurable. To look for that difference, researchers build exquisitely delicate instruments. In a typical setup, a tiny metal mass is brought extremely close to another carefully shaped mass, with a gap of only a few micrometers. The apparatus sits in an ultra-high vacuum to remove stray air molecules. Temperatures are lowered to suppress thermal jitters. Magnetic shielding blocks invisible pushes from ambient fields. The entire device rests on vibration-isolated stages, so that footsteps in the hallway or distant traffic cannot masquerade as a signal. A narrow laser beam watches for motion reflecting from a mirror attached to the small test mass. If gravity at this range behaves exactly as expected, the oscillation pattern follows a precise curve. If it deviates by even a tiny fraction, the laser trace will shift in a telltale way. Detecting this shift is like listening for a feather to land during a storm. Every source of noise must be identified and stripped away, until only the faint pull remains. So far, measurements have upheld the classic rule down to tens of micrometers. Within current sensitivity, the force still weakens with distance, just as the old law says. Yet the search continues because even a slight mismatch would be revolutionary. A confirmed deviation could point toward extra spatial dimensions curled up at scales too small for light to explore. It might also hint at new particles or forces that standard high-energy experiments have not yet revealed. These tabletop trials are modest in size but vast in implication. They test not only a centuries-old law, they test an assumption about the structure of space itself, that space is smooth, uniform, and the same at every scale. If the inverse square pattern holds perfectly, the message is stability geometry remains simple even in the realm of micrometers. If it falters even slightly, the door opens to deeper architecture, where hidden folds or new fields shape gravity in ways we have never seen. From here, the logic widens. A laboratory bench can ask questions about dimensions we cannot visualize, and the universe in turn offers natural experiments far beyond any table or chamber. When a theory reaches the limits of what laboratories can measure, the universe itself becomes the next laboratory. The tests we perform on tables and cryogenic platforms are only miniature rehearsals of something far grander, experiments that nature has been conducting for billions of years, written across the sky in the language of light and gravity. The next question in our search for a unified theory is no longer confined to glass chambers or laser beams. It unfolds in the vast unshielded laboratory of the cosmos. Out there, stars collide, black holes merge, and space-time ripples under forces beyond human reach. Each of these events pushes physics to its breaking point, stretching every equation we have. They are stress tests for reality itself, and for any candidate of a theory of everything. Among all possible cosmic experiments, one phenomenon stands out: gravitational waves. They are distortions in space-time waves that travel at the speed of a light produced when massive objects accelerate or collide. Einstein predicted them more than a century ago as a subtle consequence of his equations of general relativity. For decades, they remained theoretical, far too faint for instruments to detect. But the mathematics was clear: if the universe truly bends and flexes as Einstein described, those ripples must exist. Think of space-time as an ocean, vast, dark, and almost still. Every orbiting star, every spinning black hole sends out waves across its surface. They spread for millions of light years, faint but unbroken, carrying the imprint of their origin. Each wave encodes a story: the masses that collided, the distance they traveled, the moment when geometry itself vibrated. For a physicist, detecting these waves is like listening to a symphony being played by the cosmos. Every frequency corresponds to a specific instrument: neutron stars beating like drums, black holes roaring like deep brass, and sometimes the faintest high note, a tremor that could reveal new physics. The task is not only to hear the music, but to notice the one note that doesn't belong, the off-key vibration that no theory yet predicts. To capture these cosmic harmonies, massive detectors like LIGO and Virgo stretch their arms for kilometers, using laser light to measure displacements smaller than a single proton's width. They convert the silence of the vacuum into sound, revealing the rhythm of space-time itself. When a gravitational wave passes through Earth, it subtly stretches and squeezes the planet, ever so slightly altering the length of those arms. The resulting pattern, the faint interference of light, becomes a musical score, a recording of the universe testing its own laws. And this is the key. Where tabletop experiments probe gravity in the smallest corners of space, gravitational waves let us test it in the most violent extremes. Both are mirrors facing each other, one reflecting precision, the other magnitude. Together they define the boundaries of our understanding. In the end, every search for unity returns to the same contrast: the stillness of human instruments and the vastness of cosmic ones. For centuries, our laboratories have been temples of precision: clean rooms, steady lasers, vacuum chambers quieter than deep space. There, gravity is whispered about in micrometers, and piconewtons, its quantum nature, teased from near silence. But no matter how refined the experiment, there is a limit to what we can touch. Beyond that threshold, the universe continues the experiment for us. While we measure faint forces in a tabletop chamber, nature is conducting its own colossal tests. When two black holes spiral toward each other, their combined mass, tens of times that of the sun, curves space-time so violently that waves of gravity surge outward across billions of light years. These waves pass through galaxies, dust clouds, and clusters, carrying with them the record of cosmic collisions older than life itself. Every one of them is a pulse of pure geometry, a tremor in the very fabric that defines distance and time. To detect them, we no longer need to build collisions, we simply need to listen. Our telescopes and interferometers have become ears pressed against the surface of reality, waiting for the moment when space-time itself begins to hum. Each signal is not only a discovery, it is a dialogue, the universe answering the questions our equations have been asking for 100 years. It is almost poetic that after so many decades of searching for the smallest proof of quantum gravity, confirmation may arrive not from particles in isolation, but from the cosmos in motion. Nature seems to prefer scale, what we fail to see in the lab it reveals in the stars. Every merger, every ripple becomes a live demonstration of the same equations we test in silence. And yet these cosmic signals do more than confirm, they challenge. They test relativity, quantum theory, and every attempt at unification, stretching our formulas until they either hold or tear. They are the universe's own version of peer review, so now we turn outward. From vacuum chambers to celestial theatres, from micrometers to millions of light years, the stage expands. The hum we're about to hear will not come from a machine, but from space itself resonating with the proof of Einstein's vision. It began with a faint vibration too small to feel too brief to imagine. On September 14, 2015, two detectors half a world apart, one in Louisiana and one in Washington, recorded a signal that lasted less than a fifth of a second. To most instruments, it would have been nothing more than noise. But to the Laser Interferometer Gravitational Wave Observatory, known as LIGO, that flicker was history itself passing through the Earth. The data showed a pattern of rising frequency and amplitude, a perfect chirp, the predicted signature of two black holes spiraling into one another. Each hole was about 30 times the mass of the Sun, and as they merged, they converted a few solar masses directly into energy in the form of gravitational waves. For a moment, briefer than a blink, those waves carried more power than all the stars in the observable universe combined. Then, after traveling for over 1 billion years, they arrived here, stretching and compressing space-time by a fraction of the width of a proton. Einstein had foreseen such ripples in 1916, but even he doubted they could ever be detected. A century later, his equations found their echo in the quiet hum of LIGO's laser beams. The detection confirmed one of the last untested predictions of general relativity, not in the gentle curve of starlight, but in the violent roar of collapsing space. To make this possible, engineers had turned the theory into precision. Each LIGO arm extended for 4 kilometers, the lasers aligned so perfectly that they could sense distortions smaller than 1/10,000th of a proton's diameter. When a gravitational wave passed through, the difference in arm lengths caused the beams to interfere a faint oscillation of light that revealed the heartbeat of space-time itself. The 2015 detection, later named GW1564, was only the beginning. In the years that followed, dozens of similar events were captured: black holes merging in distant galaxies, neutron stars colliding and releasing both gravitational and electromagnetic waves. These cosmic symphonies gave birth to a new field, multi-messenger astronomy, where telescopes and interferometers work together to watch and listen to the same event. Each detection tested relativity under extreme conditions. In places where gravity is strongest, time slows most dramatically, and the boundaries between physics and singularity begin to blur. So far, Einstein's theory has survived every test, predicting each waveform with uncanny accuracy. But beneath the triumph lies a quiet tension. The same precision that confirmed his equations has also revealed their limits. We can measure spacetime's vibration, but not yet the quantum fabric beneath it. Each gravitational wave validates the map we already have, and yet hints that there is still another layer 1 hidden within the very smoothness that makes the theory work so well. Each new gravitational wave detection was more than a celebration. It was a trial. Every signal that reached Earth carried not only the story of a distant merger, but also a silent question: is Einstein still right? The LIGO and Virgo observatories became the universe's most patient interrogators. They listened to the faintest tremors in spacetime and compared them relentlessly to the predictions of general relativity. Every curve, every rise and fall of the waveform became a test of truth. If even one pulse arrived with the wrong shape, if one crest traveled at the wrong speed, the entire theoretical foundation of the modern physics could have cracked. Einstein's equations had predicted 2 very specific types of gravitational wave motion, 2 ways that space could stretch and squeeze as a wave passed through. These are called polarizations. Imagine a tiny ring of particles floating in space. as a gravitational wave washes through the ring, alternately elongates in one direction and contracts in another, first along one axis, then rotated 45 degrees. That's all relativity allows two clean orthogonal rhythms, but modified theories of gravity designed to unify or extend Einstein's ideas predicted more. Some claimed that there should be scalar or vector polarizations, additional twisting or breathing modes that would make the ring of particles distort in new ways. If those extra motions existed, they would signal new fields at play, perhaps a hidden particle behind gravity itself, perhaps even clues to extra dimensions. Detectors around the planet were tuned to catch any hint of these deviations. They watched for asymmetries, for slight irregularities in timing between observatories separated by continents. If one detector recorded a subtle tilt not mirrored in another, it could mean the presence of a new polarization mode, a fresh door opening into deeper physics. But none appeared. Wave after wave, signal after signal, the universe seemed to follow Einstein's rhythm precisely. Two polarizations, no more, no less. No extra modes, no strange distortions. Just the clean, elegant geometry written a century earlier on paper. Then came a new kind of test, the test of speed. In August 2017, a gravitational wave named GW170817 arrived. It came from the collision of two neutron stars, each the size of a city but denser than atomic nuclei. The same event also emitted gamma rays captured by space telescopes almost simultaneously. By comparing the arrival times of both signals, gravitational and electromagnetic, physicists could measure how fast gravity truly travels. After a journey of over 130 million light-years, the difference in arrival was just 1.7 seconds. That difference, when corrected for known astrophysical delays, meant that gravity and light move at virtually the same speed, equal to within 1 part in 10 quadrillion. Such precision destroyed entire families of alternative gravity theories in an instant. Models that had survived for decades, those predicting a faster or slower propagation of spacetime, collapsed overnight. In a single observation, countless elegant equations turned into historical curiosities. And yet beneath this victory, an unease remains. Einstein's theory continues to dominate every test, but its very perfection has become a kind of trap. We have confirmed its predictions in every corner of observation, from planetary orbits to black hole mergers, yet we cannot reconcile it with the quantum world beneath. Two languages remain relativity's continuum and quantum discreteness, both flawless within their own domains but utterly silent toward each other. It is the most frustrating kind of triumph. The more precisely we prove Einstein right, the harder it becomes to find what lies beyond him. The equations that describe the universe so beautifully may also be the walls that confine our imagination, and so the detectors keep listening not just for new signals but for imperfection itself. Because somewhere hidden among the perfect harmonies of space-time may lie the one discordant note that begins the next revolution. The waves we have detected so far tell a story of elegance and consistency. But hidden within that perfection may lie traces too faint for our current instruments to resolve tiny fingerprints left by the quantum structure of spacetime itself. Physicists call them quantum imprints, subtle deviations in a gravitational waveform that could only arise if gravity, like light, obeys the strange rules of quantum mechanics. Imagine a wave traveling across the universe for billions of years. As it passes through the emptiness between galaxies, it is not moving through a smooth vacuum. At the smallest scales, that emptiness is thought to flicker, with quantum fluctuations, virtual particles appearing and vanishing in a heartbeat shorter than any measurable time. Every ripple in spacetime must cross this restless sea, and as it does, it could pick up minute distortions, phase shifts so delicate that they would appear as tiny imperfections in the shape of the wave when it reaches Earth. In principle, these distortions could be read like a code. Each carries information about how gravity interacts with quantum fields at the Planck scale, where distances shrink to about 10 to the minus 35 meters, and energy densities reach levels beyond any conceivable experiment. At that scale, the fabric of spacetime might no longer be continuous, but granular, a network of discrete units like pixels forming the illusion of a smooth screen. If so, the passage of a gravitational wave through this granular texture could slightly scatter or delay parts of the signal, leaving a pattern, a quantum aftertaste within its otherwise classical waveform. Detecting such an imprint would require extraordinary sensitivity. Current observatories, LIGO, Virgo, Cagra, are magnificent, but their precision remains far from what is needed to perceive those microscopic scars. The next generation, however, is being designed for that very task. Projects like LISA, the space-based laser interferometer space antenna, will stretch detectors across millions of kilometers in orbit, listening for deeper, lower frequency waves that terrestrial instruments cannot hear. Meanwhile, the proposed Einstein telescope and Cosmic Explorer aim to reduce terrestrial noise by going underground, or expanding arm lengths to tens of kilometers. With their improved sensitivity, even the faintest phase irregularities, those slight mismatches in the rhythm of spacetime, might finally become visible. The hope is to catch something that does not belong, a tiny deviation in the wave's smooth decay, a soft beat out of sync with relativity's score. That could be the whisper of quantum gravity, a sign that spacetime itself vibrates with uncertainty, that information and geometry are woven together. Yet such a detection would bring paradox as well as triumph. For decades, gravity has been the one force that refuses to reveal its quantum side. Finding those imprints would mean that spacetime, the arena for all physical events, is not a static stage but an active participant, a dynamic entity that fluctuates, entangles, and evolves like everything else. The smoothness of Einstein's continuum would give way to the shimmering fabric of probability, and so physicists now stand in quiet anticipation. They tune their detectors, lower the noise, and prepare for the next whisper from the universe. Perhaps the next wave we catch will not be perfect. Perhaps buried in its trailing edge will be a shimmer too irregular, too delicate to fit our current theories. That irregularity, if found, would not destroy relativity. It would complete it. It would reveal the first trace of a deeper truth, that even gravity, ancient and universal, is not immune to the trembling uncertainty that defines everything else. All the waves we have detected so far are single notes, brief distinct events like isolated strikes of a drum across the cosmic distance. Each came from a specific collision, two black holes merging two neutron stars spiraling into one another, each announcing its own moment of creation and collapse. But beneath those loud, transient bursts lies something quieter, older, and vastly more profound, a stochastic background, the unending hum of the universe itself. Unlike an individual signal, this background is not one event, but the combined echo of countless events layered together. Every merger, every collapse, every violent fluctuation of space-time has contributed a faint trace to the fabric of the cosmos. Over billions of years, those traces have overlapped and blurred, forming a sea of gravitational murmurs that now fills all of space. If we could isolate and decode this background, we would be listening to the earliest memories of the universe, a record older than light itself. Physicists describe it as a kind of gravitational noise, but it is not random in the ordinary sense. It carries patterns, statistical fingerprints of how matter, energy, and spacetime interacted in the universe's formative epochs. Embedded in that hum could be the answers to questions that no telescope or particle collider can reach. Was the early universe shaped by cosmic strings, hypothetical one-dimensional defects left from symmetry breaking? Did primordial black holes form before stars were born? Did inflation, the rapid expansion after the Big Bang, leave ripples that never fully faded? Each of these possibilities would leave a slightly different spectral texture in the stochastic background's faint continuous song. Detecting it is one of the grandest challenges in physics. The signals are unimaginably weak, their amplitude smaller than the vibrations caused by atoms striking the mirrors of our detectors. To hear them, scientists must use statistical listening, collecting data for years, averaging the random until the pattern of something universal slowly rises above the instrumental noise. Projects like LIGO, Virgo, Cagra, and future observatories such as LISA or pulsar timing arrays are now synchronizing across the globe to identify this collective signature. Instead of listening for a single wave, they listen for the entire ocean, and here lies the bridge between observation and theory. If the stochastic background can be measured with enough precision, it could act as a cosmic fingerprint test for the theory of everything. Different unification models, string theory, loop quantum gravity, emergent spacetime frameworks predict subtly distinct spectral slopes and polarization mixes in that background. Even a slight deviation in its frequency distribution could confirm or eliminate whole categories of theoretical possibilities. What we call noise might in truth be the coded language of creation. To read it would be to read the collective heartbeat of the cosmos. And perhaps hidden inside it there is the trace of something deeper than physics itself, the transition from the universe's ordered laws to the randomness we perceive today. As detectors grow more sensitive, we move closer to hearing that low, omnipresent murmur directly. It would be the sound not of an event but of existence continuing a vibration without beginning or end. And so we stand at another threshold. We have listened to the sharp notes of cosmic collisions. Now we prepare to listen for the symphony beneath them. This hum, the oldest and faintest in all creation, may not only distinguish between competing theories, but also point toward a truth more unsettling, that the universe itself might be a process of emergence, a reality still forming, still singing, woven from the resonance of everything that has ever been. At some point, every search for a unified truth runs into a mirror. We look at the reflection of our theories and they begin to look back, questioning the assumptions that made them possible. The deeper we chase the dream of a single perfect equation that explains everything, the more we encounter the possibility that everything might be too large, too complex, too self-referential to ever fit inside one frame. This realization is not new. In the early 20th century, the mathematician Kurt Gödel demonstrated that even the most rigorous logical systems contain truths that cannot be proven from within those systems. Every consistent mathematical framework, no matter how complete it seems, leaves something unspoken, a statement that is true but unprovable inside its own rules. It was a shocking idea that incompleteness is not a flaw, but a feature of any self-contained universe of thought. And it left a quiet question hanging in the air. If this is true for mathematics, the purest logic we know, could it also be true for physics? If so, then the quest for a theory of everything might carry a hidden paradox. The more completely it tries to describe the universe, the more it may reveal the boundaries of description itself. Perhaps there will always be truths that exist just beyond the edge of the formal system, realities that can be sensed but never fully written down. Physicists have begun to ask, what exactly does everything include? Is it only the four fundamental forces, gravity, electromagnetism, the strong and weak nuclear interactions? Or should it also include the emergence of life, of mind, of consciousness? If so, can an equation really contain awareness, complexity, or meaning? Each layer of reality, physical, chemical, biological, psychological, operates by its own rules, woven together but not reducible to one another. To compress all those patterns into a single formula might be as impossible as trying to build a microscope that also functions as a telescope. The same lens cannot reveal both the quantum grain of spacetime and the structure of galaxies a billion light-years away. This is the paradox of scale, that clarity in one domain may require blindness in another. Every theory is a lens, and every lens magnifies at the cost of distortion. When we seek to unify, we must decide what kind of resolution we're willing to lose. Even Einstein's elegance, even quantum theory's precision, are partial views of something larger, layers in a structure we can sense, but not fully chart. Some thinkers now suspect that this layered structure is fundamental. Reality may not be a single code waiting to be cracked, but a hierarchy of descriptions, each valid within its own range. Gravity may belong to one layer, quantum behavior to another, and consciousness to a still higher stratum of emergent organization. The search for unity, then, is not about erasing boundaries, but understanding how these boundaries connect. In this light, Gödel's theorem becomes not a barrier, but a guide. It reminds us that wholeness may not mean compression. Perhaps the universe was never meant to fit inside one box because its nature is recursive, each level containing echoes of the others, each truth pointing to the next. So when we speak of everything, maybe we are not naming a single equation, but the endless relationship between equations, a conversation between layers of law. And in that conversation, the cosmos remains both complete and unfinished, always slightly beyond the reach of its own understanding. If unity cannot be found in the equations we already know, perhaps it lies beneath them. In recent decades, physicists have begun to wonder whether space-time itself, the very stage on which all events occur, is not fundamental at all. What if the arena of reality is a construct, an emergent pattern born from something deeper and simpler? The idea began not with poetry, but with mathematics. Quantum theory describes entanglement the way two particles can share a single state, even when separated by vast distances. General relativity describes geometry, how matter and energy bend the fabric of space and time. For years, these two frameworks seemed unrelated, one probabilistic and discrete, the other continuous and smooth. But a growing number of researchers now suspect that geometry may arise from entanglement itself. In this view, space-time is not the background. It is the byproduct of information connecting everything to everything else. Imagine a vast web where each thread represents a quantum correlation. Where the threads are densely interwoven, geometry appears, distances, directions, curvature. Where they thin out, space seems to stretch. Where they break, space-time itself may tear. This is emergent space-time, the idea that the universe is not made of matter resting in space, but of relationships that, when sufficiently complex, become space. One mathematical embodiment of this concept is the holographic principle. It suggests that the three-dimensional universe we experience could be a projection of information encoded on a distant two-dimensional boundary. Every atom, every galaxy, every second of your life might correspond to bits of information written on a cosmic horizon. To describe reality, then, is not to chart where things are, but to decode how information is arranged. The holographic idea is not metaphor. It has precise mathematical forms such as the AD-CFT correspondence. There, a universe with gravity inside a volume is exactly equivalent to a quantum field theory on its surface. What looks like curvature and motion within space emerges from patterns of entanglement on the edge. In this sense, reality is data. First, geometry, energy, and time are consequences, not ingredients. Other frameworks explore the same intuition through different languages. The causal set approach imagines the universe as a network of discrete events, linked by cause and effect like digital spacetime, where continuity is only an illusion that appears at large scales. The twister theory of Roger Penrose tries to build spacetime from light itself, treating photons as the most elementary entities from which positions and durations are reconstructed afterward. Each of these visions inverts the traditional hierarchy of physics. Instead of matter in motion, generating information, information itself generates matter and motion. Even the much-discussed simulation hypothesis belongs to this family of ideas. It does not claim that we are literally inside a computer, but it acts as a mirror reminding us that laws of nature could themselves be code, and that physical reality may just be a higher-order description of informational processes. If these models are true, then what we call spacetime is only one layer of representation, a shadow of something richer, a network of logic and probability whose texture gives rise to form. To understand it is not to step outside the simulation, but to recognize that the simulation is the universe. And if spacetime itself can emerge, then perhaps unification does not mean finding one equation, but discovering how patterns of information give rise to the world we see. At the edge of physics lies a strange commandment, one that seems almost moral in tone. Information must never be lost. Even when a star collapses into a black hole, even when light itself can no longer escape, the universe appears to keep the record. What falls inward is rewritten, encoded in subtle distortions at the horizon. Energy may fade, matter may dissolve, but the pattern, the information, remains. This is the quiet lesson of the black hole information paradox. Stephen Hawking once showed that black holes emit radiation slowly evaporating into nothing. But if they truly vanish, where does the information go? Quantum mechanics insists that every state, no matter how chaotic, must evolve in a way that preserves information. Relativity, meanwhile, seems to allow its disappearance behind the event horizon. The tension between these two truths has become a mirror, showing that the deepest law may not concern matter or space, but the continuity of information itself. We once believed the universe was built from particles and fields. Now it may be more accurate to say it is woven from relationships, from the correlations that tell one quantum where another has been. Information is not a byproduct, it is the thread. Every photon that leaves a distant star, every gravitational wave whispering through detectors like LIGO, every quantum entanglement in a lab cryostat, all of them participate in the same exchange and endless circulation of encoded meaning. If this view is right, black holes are not tombs but libraries. They compress the history of what they consume, storing it in microscopic fluctuations of their surface area. And perhaps the universe itself is such a library, not a single story, but a vast index of interlinked descriptions. Each law, each equation is only a chapter in a book that cannot be closed. So maybe the ultimate theory, the long-sought everything, is not a line of mathematics, but an architecture of memory, a structure of transformation that tells us how information flows, never dying, only changing its form again and again. Take a slow breath. The story of science has never been a straight line. It is a trail of attempts of questions that refuse to die. And even when the grand equations broke apart, they left something behind: tools, insights, instruments of precision that still guide us. Think of the bootstrap, born from the idea that symmetry itself could define what is possible. It tells us that even without a full equation, we can outline the borders of all consistent theories. A compass made of logic still pointing north when certainty fades. Then there are scattering amplitudes, the quiet heartbeats of particle physics. Once just numbers, now they reveal hidden geometry shapes called amplituhedra, multi-dimensional crystals where probability becomes pattern. The universe, it seems, prefers elegance not in sentences but in shapes, and the holographic principle, our most daring bridge between gravity and quantum reality. It whispers that everything we see in 3 dimensions could be written on a distant 2-dimensional boundary, a memory etched on the edge of existence where information creates gravity, and the fabric of space-time is only a projection of deeper order. In laboratories, the entanglement experiments continue tiny weights, floating in near-perfect vacuum, their fates linked only by gravity. If they ever become entangled, it would mean that even gravity obeys quantum law, a small fragile sign of unity waiting to appear. And above us, the gravitational wave observatories keep listening, great ears made of laser light. Since 2015, they have heard the faint tremor of space itself, waves born when black holes collide. Each signal is a message from distances no telescope can see, proof that Einstein's geometry still sings through the dark. All these are fragments, yes, but fragments that endure. Together they form the working vocabulary of curiosity. They are not the theory of everything. They are the instruments that keep the search alive. When you listen closely, you can hear the same pulse beneath them. All symmetry, geometry, vibration, connection. Different voices, one rhythm. The rhythm of a universe still unfolding. Here lies the quiet paradox. If we ever reach the final equation, the one line that explains it all, would the story still be worth telling? Perfection closes the book. It freezes the conversation. Science at its heart is not a monument of answers. It is emotion, a living dialogue between doubt and discovery. Each failed attempt has been a revelation in disguise. Every theory that broke apart showed a new way of seeing. The beauty lies not in completion, but in the act of continuing. So we keep asking. Not because we expect to arrive, but because every question redraws the map of what can be known. If success means silence, then failure is the universe's way of keeping us awake. The equations crumble, the measurements drift, but the wonder stays. We are not mapping perfection. We are tracing the edges of mystery, and the edges keep moving. That motion, that refusal to end, is the real definition of life within thought. A story that breathes only as long as it remains unfinished. Imagine for a moment that knowledge is not a mountain to climb, but a library, infinite quiet, softly lit. Every shelf holds a different way the universe has been understood. Some volumes are thick with equations, others whisper with metaphors. None of them alone are the truth, yet each carries a piece of it. Walk with me between those shelves. On one side lies Newton's Principia, where motion and gravity are joined by a single law. On another, Einstein's relativity, curving space and time into a smooth geometry. Farther down, the slim, restless books of quantum mechanics, filled with probability and shimmer. And above them, newer manuscripts still being written. Holography, emergence, information theory, ideas so fresh the ink has not dried. Look closer. You'll notice that the pages sometimes overlap. Equations echo each other, as if they are translations of a single text written in many dialects. This is how the universe communicates, not in one tongue, but in harmony through difference. Science and philosophy are the two eyes that read these pages. Science asks, is it true? Philosophy asks, what does it mean? When one eye closes, depth disappears. When both are open, the image gains dimension. Through the scientific lens, we see structure fields, forces, the measurable. Through the philosophical lens, we feel context, purpose, relation, belonging. One describes the world, the other reminds us that we are part of it. Together they form the dual lens of understanding, a fusion of precision and wonder. Perhaps the theory of everything is not an equation at all, but the architecture of this library. Each theory a book, each book a perspective, and together they compose the full atlas of what reality can express. No single map can hold all terrain. The universe is too varied, its scales too immense. At the quantum level, space-time itself vibrates with uncertainty. At cosmic scales, it stretches into curvature. Between them lies life, the bridge where matter becomes mind. If the cosmos resists compression into one law, it may be because it thrives on plurality, not contradiction, but polyphony. A chord needs many notes. Reality may need many frameworks. The harmony arises not from sameness, but from the resonance between differences. Close your eyes Listen. Do you hear it? The faint hum between ideas, the pulse connecting thought to observation, the breath between question and answer. That is the sound of the universe thinking. You and I are part of that thought. Every time we look up, every time we measure or wonder, the library expands by one more page. We are both the readers and the authors. In the end, science is not about control. It is about participation. To measure the universe is to join its rhythm, to let curiosity mirror creation. Knowledge does not sit outside reality. It grows within it like stars forming from the dust of older stars. If you stand very still, you can almost feel the turning of that cosmic page, the quiet transition from what is known to what is only just beginning to be imagined. Each discovery becomes a bookmark, each mystery a chapter not yet written. Perhaps this is how the universe endures, not through permanence but through reinterpretation. What was once a question becomes an instrument. What was once a failure becomes a map. And so the library never closes. We keep adding to it with equations, with experiments, with dreams. The oldest pages glow faintly with starlight. The newest are blank, waiting for the next hand to write. As long as we do, the story continues. The cosmos keeps writing and we keep reading together between the stars.